Welcome back. This is the last of the 10 lessons on equilibrium reactions, and we are going to discuss useful equilibrium constants, in specifically solubility and ionization constants. So what is the solubility product? Hypothetically, a saturated salt solution like we have discussed, I think in lesson 7, could be described by this dissociation equation. Salt AB is in equilibrium with the ion A plus and the ion B negative in a solution. Now, this solution or the dissociation process is usually endothermic. So we're working with a saturated solution. So the Kc for this reaction or process will only depend on the concentrations of the cations and the anions, because AB is a solid. So the concentration of AB can't change. So we call Kc the Ksp, meaning the solubility product of the dissociation of the salt. So solubility product is the Kc value for salts in solution, where it would depend only on the concentration, the product of the concentrations of the ions in the solution. If the salt is very soluble, Ksp would have a high value. If the salt is hardly soluble, like calcium hydroxide, which is only slightly soluble, the Ksp, the solubility product, will be a very small value. So a dilute solution will have a constant value less than Ksp. If you have a dilute salt solution, not a saturated salt solution, the Ksp or the solubility, the product of the ions concentrations of the ions will be less than Ksp. The ionization constant for acids, the hypothetical reaction for an acid ionizing in water is given here. H represents the hydrogen ion. Ha dissolved in water, a liquid, will be in equilibrium with the oxonium ion as well as the acid anion. This is usually an exothermic reaction. Kc for this becomes Ka, the ionization constants for acids. So it would depend on the product of the concentrations of the oxonium ions and the acid anion divided by the concentration of Ha. Left the brackets out there. That's naughty of me. It's the concentration of the acid. Right. So Ka for a strong acid is usually a very high value because the acid ionizes completely in the water. So like sulfuric acid, the ionization equation would be H2SO4 in solution plus two waters because the sulfuric acid has two protons to donate. It will form two oxonium ions and the sulfate ion. So the Ka for this would be the concentration of the oxonium ion to the power 2 times the concentration of the sulfate ion divided by the concentration of the H2SO4. And this value is around 1 million because the sulfuric acid ionizes completely. That's why it's classified as a strong acid. Next we look at the Ka for weak acids like the ethanoic acid. The ionization equation is given as CH3COOH aqueous because it's dissolved in water. Water is a liquid. It's in equilibrium with H3O plus, the oxonium ion, and CH3COO negative, the anion. Now, the Ka expression is given there, and we know that weak acids hardly ionizes, so your concentration of ethanoic acid, the whole molecule, will be much higher than the concentration of the oxonium ions and the acetate anion. So here you would have like a Ka value around 10 to the power minus 5. Compare that to the Ka around 10 to the power 6 for sulfuric acid. You see the difference between the Kas for weak compared to strong acids. Lastly, we're going to look at the ionization constant of water. Now, you've never before considered water to be ionizing or dissociating into ions in itself. So this is brand new, a brand new concept for you. So at 25 degrees Celsius, the scientist tells us that water ionizes to form the hydrogen ion and the hydroxide ion. So there, if the temperature is kept constant, the water molecule, liquid, is forever in equilibrium with H plus and OH negative. Now, water is an extremely weak acid in this case. Acids form protons, the hydrogen ions. So the Kc value for water would depend on the concentration of the hydrogen ion and the concentration of the hydroxide ion. But it's not called Kc anymore, it's Kw. So Kw would be the concentration of the hydrogen ion times the concentration of the hydroxide ion. And this value is actually very, very small. It is 10 to the power negative 14. And I'm going to show you something in the next chapter when we see each other again. So it's Kw for water, and the value is something like 10 to the power minus 4. So the concentration of the hydrogen ion is always equal to the concentration of the hydroxide ion in the water, because the ratio, the mole ratio, is 1 to 1. So the 10 to the minus 14 must be you take the square root of that, and you get 10 to the minus 7 as the concentration of hydroxide and hydrogen ions, which is like a 10 millionth of a mole. So the equilibrium constant, Kw for water, is 10 to the minus 14.